So today's focus is all going to be about space physiology, and which is a topic we have not covered yet so far. So we're very excited to have two experts in the field. Before we get to that, I just want to promote a Christmas social that Dr. Ella Walker is organizing for tomorrow at 18:30 hours in London. So you see the Zoom meeting invite there. There's going to be time for a trivia quiz that a few individuals have submitted. So there'll be various rounds there too. So it's a chance for us to informally socialize. And again, if you need to get the link, again, you can check on here, or else you can go on Twitter and contact Dr. Ella Walker at Ella_Walker. And it's also one of her pinned tweets if you find her. So hopefully we'll see some of you tomorrow afternoon. So our series, we started in April, shortly after the lockdown, thanks to Chris Tyler's initiative and also with Today Debevich. And as you see, our wall of fame has been growing. So we've been very, very pleased with that. We now have over 30 speakers, I think 34 total speakers over the sessions that we've organized in 2020. And we'll have more coming up in the new year, starting again on January 7th. A reminder that all of our talks are available online, and you can find them at icee2021.com/past-events. And you'll see on there, if you go to icee2021.com, you'll see the link for past talks. If you click on that, you will see all of the talks in full. And also in most of the talks, our speakers have been very kind in providing for us student handouts also. Sometimes they're a joint handout, sometimes they're individual ones. And they've been a great resource for teaching, whether at the undergraduate level or also at the graduate levels. Besides a summary of the talks, they have also provided discussion questions or some case studies to raise in class. So they've been a great help. I know I've used these series quite a bit in my undergraduate and graduate teaching this past semester. So today it's going to be, again, all about space physiology. For Canadians, it's also a very historic day because it was just announced yesterday that Canada has secured 2 flights in the coming lunar missions on the Artemis missions, including one on Artemis 2 in 2023, which will be very much like Apollo 8 in the 60s. It will be the first one to circle the moon with manned spaceflight. So with that, I'm going to pass over to our 2 speakers today, who is Dr. Brigitte Ganz and also Dr. Julia Attias. And we will be having Dr. Ganz speak first. And then, as always, we have the Q&A tool that we hope you can interact with us using that by asking questions. After Dr. Ganz finishes her talk, I'll present or moderate a few of those questions, and we'll pass it on to Dr. Attias. And then afterwards, again, we'll have some questions and also a group discussion. So with that, I'm going to invite Dr. Ganz to start sharing her screen.
Yes, I will. Hello, everybody. Can you see my screen?
Yes, we can.
Fantastic. So hello and welcome to my talk. My name is Brigitte Ganz. I'm actually German, so please excuse my English. Currently working at Manchester Metropolitan University in the UK. And my research topic is spaceflight and space physiology especially. And that's how it comes that they asked me to give a talk today. And actually, I usually give a full lecture series about space physiology and medicine that consists of 10 long talks. So this is just a brief overview today that I can give in 20 minutes because it's such a broad field and there is just so much to say about the topic. But if you have further questions, let me know. Feel free to ask, or if you want to dive more into the topic, I'll show you some options at the end. Why doesn't this move? Okay, here we go. So I just briefly wanted to introduce myself so you know who's speaking. I'm an orthopedic surgeon and a physiologist, and I know that's strange for people coming from the Commonwealth, but in Germany, physiology is a medical residency, so it's a specialization of medical doctors other than a separate course at university. In Germany, you cannot study physiology at university, so you'd always be a medical doctor and then do a 4-year residency on top of it. And I've done these 2 residencies, and currently I've got a fellowship grant of the German Research Council to do space research in a bed rest study with NASA and the European Space Agency ESA. We did this bed rest study last year, and Julia Attias, the next speaker, was also involved in that study. And my research topic is space medicine, and in particular the musculoskeletal system in spaceflight, in immobilization, and also in aging, because there are a lot of overlaps within the fields. And I've previously worked at the Center for Space Medicine in Charité University in Berlin, in Cologne University Hospital in Germany, and German Aerospace Center, DLR, which is kind of the German space agency in Cologne, and in RWTH Aachen University Hospital in Aachen, Germany. But let's start into the topic. So what is different from the Earth, or what is different when we're in space? So first of all, we've got weightlessness, which is super unusual for the human body, and I'm going to talk about that a lot. But then we also have hyper-G at launch and landing, which means hyper-G, so 1G is the gravity on Earth, and hyper-G is when we've got much more gravity than that. It comes with a lot of strain to the physiological system. We've also got radiation, and I'm not going to dive into that topic today because it's an entirely different and really big field, but it's super relevant, especially when we look at the flight to Mars or long journeys into our solar system that might take several years. And currently the large international space agencies are planning a new space station in the cislunar orbit that will be called the Gateway Space Station. And that will be outside the Earth's magnetic field, which means that space particles and or space radiation will reach the humans who are there. And that has only once in history been the case, during the Apollo flights to the moon. And the last, as you all know, probably the last Apollo flight was in the early 70s. And after that, nobody has left the Earth's magnetic field. So nobody has ever done research on what the radiation that is out there will really do to the human body. And so this Gateway Space Station will mainly be used to do research on the radiation effects initially. And that is going to be a very exciting chapter in human physiology coming up. So yeah, I'm very excited to see if it's all as feasible as people think, or if there are maybe more problems associated with radiation. So I'm not going to talk about radiation anymore in this talk. I just wanted to lose a few words about it to give you an idea. Then we have isolation, confinement, and a very tight schedule. Those are stressors, massive stressors. Isolation leads to psychological and social issues among the crew. Also a huge topic, but today I'd rather talk about physiology and not about this. And then we have limited resources like food and drinks or medicines. For example, when you've eaten all your favorite food, it's gone and there will be no more of it. Or if you've used up all of the medicines for one very sick person in the crew, there might be nothing left for another disease or another problem. And these are things that really need to be considered when planning a space mission. Then there are gases and toxins, smells in artificial environments that are quite serious when you're always exposed to them. And there's also constant noise in spacecraft and space stations, actually really loud, coming from a lot of technical systems that are constantly running, and you really can't turn those systems off. The neutral body posture in weightlessness looks approximately like a nerd sitting in front of the computer with the arms moving to the front and the legs also bending and moving to the front. And this is due to the muscle and tendons just automatically bringing the body into this posture. And this is an overview of roughly what's happening, or several things that are happening. And I have picked a few of them for today's talk. So one of the big issues at the moment that most research is focusing on is impaired vision. That has only been realized recently. So in the first years of human spaceflight, nobody ever reported problems in vision. But it's interesting that a lot of astronauts have now had blurry vision, and there have been longer lasting problems also when back on Earth. So this is a huge topic, and currently there are some theories dealing with pressure coming from the back of the eye, or also with thromboembolic events leading to impaired vision. Then there's space adaptation, back pain. I will talk about that in my talk. There's bone and muscle wasting. That is actually one of Julia and my main topics we're working on. And it's important to do to have countermeasures ready in place for that. And Julia is going to talk about that a bit more in her talk. That is after mine. And then when you lose a lot of bone mass or bone calcium, and you don't have proper countermeasures in place, you will develop kidney stones. And kidney stones have been a serious issue in the past during space flights, and some space flights even had to be terminated earlier, and people had to fly back because of problems due to kidney stones. So that should not be underestimated. That is a serious issue. Then we have changes in muscle tissue. Actually, there are different types of muscle fibers in the muscle, and the endurance fibers, the slow twitch fibers, will turn into power fibers, into type 1 fibers. So that is quite interesting, and that is something we've recently worked a lot on. Then we have a fluid shift, because the gravity is not pulling the fluid into the legs anymore. It will move into the head and chest region, and there it causes a puffy phase, and of course the legs are very thin then. We've also got a decreased blood pressure, and decreasing blood pressure by about 10 millimeters mercury in a few months in space. So it's not very much, but in case you tend to have a very high blood pressure, that's good news, I think. So there's fainting here, because when you come back to Earth and you've adapted to space, I will explain that in the next slides, there might be a problem with fainting. And then another thing is the heart shrinks. The heart muscle does not have to pump as much as on the ground with gravity. And so it's everything that is not used as much will be reduced by the body. So we've actually got shrinking hearts in astronauts. What a sad story. So, but first of all, the fluid shift in microgravity. Here is an example of Hans Schlegel, a German astronaut. This is how he usually looks while he's on the ground. And this is him in the space shuttle looking at the International Space Station. And you can really see how different he looks. You would even think it's a different person. And there is the puffy face coming into action. And the same here for her. And this is just an example of bird legs, but actually you just get really thin legs, like in the morning when you get out of bed. Oops, okay. You have also got a change in taste because of the fluid shift. The taste buds will swell, and that has some effects on your perception of what you like and what you don't like. And strangely, the shrimp cocktail is the favorite dish of astronauts, and it's much more popular than on Earth. And actually, it's become almost a currency. So some astronauts and cosmonauts have been reported to exchange it against vodka or other very precious things in spaceflight, just because it's so delicious. But this is how it looks in space, packed the way it is packed up there. And I don't really think it looks that delicious, so it must be super amazingly tasty to be used as really as a currency. I think that's quite a fun story. But actually, astronauts usually get, and cosmonauts and all spacefarers, food tasting before they get to space, and they pick their dishes. And when they're up there, quite often it's a bit different than they thought it would be. And some things turn out just to be not as delicious as they used to be on Earth. So what is happening with regards to the blood pressure? So as said, there's fluid shift going upwards towards the head and chest region. And in the chest, we have pressure sensors called baroreceptors. on the aorta and also on the carotid arteries. And those pressure sensors will sense a higher blood pressure because there's just more blood volume up there. And will give this information to the brain, and the brain will cause or deliver this information to the kidney in a complicated way. And the kidney will know it has to excrete water. So one of the things that happens when you first get to space is you will pee 1.5 liters of water within the first about 24 hours. And that is what actually all astronauts do. They need to pee a lot. And also space tourists will need to go to the toilet quite a lot when they're up there. And this figure here shows, actually I can pull this aside a little bit, shows 3 blood vials. So when you take somebody's blood and you let it stand there for a while, it will separate into the cells and the serum. So this is the so-called hematocrit content. It's usually about 45% of the blood volume. And when you go up to space and you've been there for a few hours and you've peed a lot, then the relative content of cells in the blood will be much higher. So you have an increased or elevated hematocrit up there. It will normalize over a few weeks while in space. And then after return to a 1G environment, or also probably when you land on Mars, you will be very thirsty and you will need to fill up those 1.5 liters again, and then you will have a much lower hematocrit. And that goes along with the decreased ability to transport oxygen in the body. So yeah, you're just not, your endurance will be worse than usual, and you will just not be able to exercise as well as you used to before the amount of cells has normalized again. And you can see this quite often when you see people landing after a space flight. For example, here Don Pettit landing in the Kazakhstan steppe, and they usually need to be carried. Some say they don't need to be carried, but then they faint or have other problems. So the problem is really that they don't have enough blood on board, and that leads to orthostatic intolerance problems. And that's why it's quite nice to carry them actually. And in physiology, or in a physiological experiment, this translates to the following. On the left-hand side, we have a normal tilt table test experiment. Tilt table means somebody is lying on a stretcher, and then you tilt the person up to 85 degrees and measure the blood pressure and heart rate and see what happens to the person. And on the right-hand side, you can see the same test for somebody who has just been to space for a while. And let me explain what we've got here. So the red line is the heart rate, and the pink surface area is the blood pressure. That is always an area between when the blood pumps and when it doesn't pump. So the systolic and diastolic blood pressure. And usually when you tilt a person, this is all gonna stay quite stable. So the heart rate increases a little bit, but then it stays more or less stable. And the same is true for the blood pressure. But when you've just been to space and the cardiovascular system is not adapted to gravity anymore, and especially the blood vessels, they will just accept more blood volume in the legs, and the heart is a little bit smaller and cannot pump as good anymore as before the space flight, then you will see, so the black line is the tilting, then you will see the effect that the heart rate increases much more than before. It's going up to much higher levels. And initially, the cardiovascular system will be able to maintain the blood pressure, but then it's going to drop suddenly. And actually, if you don't stop the experiment, the person is going to faint with this very low blood pressure. And that is called orthostatic intolerance. So the body is intolerant to the G forces on the body. And this is something very typical. And actually, the tilt table experiment is always done pre and post flight because it's a measure of how good the training has been on the space station. And it's also used in bed rest studies and other studies that simulate spaceflight to see how well results are comparable to real spaceflight. I think that's quite fascinating. And another thing that happens when you've just landed from space is oftentimes spacefarers get G-measles, and that is not an infectious disease like COVID or anything. It's not a virus. G-measles are simply bleedings in the skin. that appear when the hydrostatic pressure is quite high. For example, during landing in a Soyuz capsule, you'll be lying on your back, so those G measles will be in the back. Or this was a person on the tilt table before and after a bed rest study, or twice after a bed rest campaign, and his blood vessels also changed a little bit during the bed rest period. And you can see that those G measles always appear in exactly the same spots because of the architecture of the blood vessels. So in case you see somebody who has a lot of those on the back, you may ask if the person has just been to space. Another really important issue is space motion sickness. When you've just arrived in space and you think, wow, I'm finally here, amazing, it usually hits in and is no fun, because there's a lot of nausea and vomiting when people have just arrived in space flight. It's quite similar to seasickness, actually. And usually the symptoms are relatively mild and they're reported to be severe in 10%, but you can't really believe what they say because a lot of astronauts don't like to admit problems as they want to fly again. So this is the officially reported numbers, but many doctors think that it might be a bigger problem in space tourists who may be not as well trained and adapted. And reasons are that there's a mismatch between the information coming from the inner ear and the visual system. And then the brain just gets terribly confused, and that leads to nausea and vomiting. And the symptoms usually disappear within 2 to 4 days. So it really takes a few days until you can start to enjoy your space flight. And due to this fact, it's also the case that you shouldn't do an EVA, an extravehicular activity, or a walk during the first days in space, because it would be really dangerous to throw up in a spacesuit. And that's why it's usually not done during the first days. And that also needs to be considered when planning tourist flights in the future. And another issue is decompression sickness. Many of you may know that from diving, because it's the same thing. When you dive up too quickly or too fast, then nitrogen bubbles will form in the blood and in the tissue and cause embolism in the blood. That means these bubbles will get into the lung and obstruct blood vessels, and may also get into reach the brain and obstruct blood vessels there and lead to neurological symptoms, for example, and that's a huge problem. And the first symptom will be bends, muscle and joint pain, because air bubbles will just collect in the joints or in the muscle tissue. And it's a threat, especially during EVAs, during spacewalks, because for example, when you get out there and your spacesuit is hit by a micrometeoroid, or there's a leak somewhere and you suddenly lose a lot of pressure, you will have exactly the same problem as in diving up too quickly. And that's why this is a huge issue. And that's why for prevention, there's a pre-breathing exercise done with oxygen on the space station. Or in the past, they did camping out, and sometimes there's still an indication to do that. That means sleeping in the airlock the night before the spacewalk in a 100% oxygen atmosphere, where the pressure slowly gets decreased over time, because it's better to have only a third atmosphere in the spacesuit compared to the space station, because then when a problem arises, it's the absolute drop in pressure is not as high, and you also can move better in the spacesuit, because when it's pumped up, it will be very stiff. Okay. And these are just some examples. This is this is an air bubble in a joint, in a finger joint. Actually, it looks like it's going to be really painful because all the structures will be stretched. And this is another thing that is typical when you have embolism in the skin. So some parts of the skin won't have enough oxygen, and that's how it looks. Okay. And now briefly, I just see that I'm running out of time. Another thing is that you grow in space about 5.5 centimeters in the first 24 hours. So that's massive. And most people get back pain, more or less, during the first week or so in space. And the mechanism is that the intervertebral discs, they are negatively charged because they contain protein, and sodium is positively charged and likes to to attach to those negative charges, and sodium always brings water with it. So the intervertebral discs between the vertebra, the bone vertebra, they will swell. Also in everyone on Earth, when you wake up in the morning, you're about 1 centimeter taller than in the evening. So that is normal. And in spaceflight, this effect just is totally exaggerated. Here, this figure shows the example of one astronaut. Is actually from the book Fundamentals of Space Medicine of Gilles Cremant, a very nice book I can recommend. Pre-flight, the person shown here was just below 1 meter, 81 centimeters. And then this is time from launch in hours. And after about 20 or 24 hours, the person had grown to 185.5. So really 4.5 or 5 centimeters taller than before. And then usually this height just stays throughout the rest of the flight. And when you come back to Earth, unfortunately, you grow back to your old size. So there's no gain. There's no gain. So everybody who's a bit smaller, don't consider going to space to grow. Doesn't work. And yeah, as I said, a lot of people in space report space adaptation back pain, and that's quite an operational issue because usually people need to take painkillers to be able to work. And you can see here that it mainly occurs during the first days, so massively during flight day 2 or flight day 3, and then it's getting less. So again, for space tourists, this is one of the things to expect when you've reached space. Let me just show 2 more slides on bone and muscle, and then I'll hand over to Julia. We have a problem with bone and muscle loss in weightlessness because these structures are just not being used. And this is a plot from a paper that compared spaceflight participants to spinal cord injury patients. And the triangles here are bone and muscle in spaceflight participants. And these 2 lines show the same in spinal cord injury people. And actually, the loss in bone mass and muscle mass is quite strong in spaceflight when you don't exercise to prevent it. And it's about half of spinal cord patients who are really only in bed and can't move at all anymore. So it's quite massive, and it's really necessary to have countermeasures that Julia will be talking about. And just a final slide on muscle volume. This is a study from 4 crew members who have spent 17 days in a space shuttle flight. And before space flight, their muscle volume of different muscles was measured. And then after landing, this is day 0, landing after the 17-day flight, it was seen that some muscles had lost more volume than other muscles, especially the gastrocnemius muscle and soleus muscle had particularly lost muscle volume, while, for example, the anterior leg or the hamstrings had lost a bit less. So there is a difference between muscles, and it's actually quite a lot here. This is approximately 87% or so of the mean pre-flight volume. So we really deal with a high loss of muscle mass. And that was my last slide. I would briefly like to advertise for my book together with my brother, who's an astrophysicist. I've published a book, the Spacefarer's Handbook, Science and Life Beyond Earth, in August this year. It's quite new, and it deals with all the space physiology, medicine, but also engineering and everything you need to know if you want to fly to space. And it contains the content of my space medicine lecture series, but also much more. And it's written for laypersons, and it's a fun read with a lot of jokes. And if you want to know more about me or reach out to me, you can always contact me through my website. Oops, I didn't want that. www.birgittaganse.de. And yeah, thank you very much for your attention. Now I'm really looking forward to hearing your questions. Thanks a lot.
Well, thank you so much, Dr. Ganse. That was an awesome introduction to the many challenges that we face in spaceflight, and both short-term and long-term. In the interest of time, we're going to move to Dr. Atias very quickly, but I just have one quick question I want to ask. Given the 4.5, 5 or more centimeters in height change, are things like spacesuits kind of sized so that
Yeah,
knowing
good point.
people are going to be hard because they're very rigid. It's not as if you have room to kind of flex or really kind of accommodate that.
Yeah, if you plan your private flight to space, just buy a bigger one. Always be prepared. Yeah, of course, so currently the space agencies know that, but a layperson might make that mistake indeed.
Yeah, but for the space agencies right now, are astronauts sized knowing that they're going to be higher?
Yeah, because it's always like that. It's just there's a slight variation between how much someone grows, so they need to be a little bit flexible and oversize them a little bit. But it's not an issue. They know. Yeah.
Super. And I guess just follow up on the spacesuits. The what's the current pressure that the spacesuits are kind of regulated at? The space station is at 760 millimeters of mercury pressure. And
yeah, it's a third of the space station pressure. So it's really quite low, and it really takes time to adapt before that. But it needs to be that low to avoid problems when having a leak in the spacesuit, and also when just to be able to move in the spacesuit, because you all know what it's like, or maybe you don't. In a costume for carnival or something like that, it might be hard to move when it's quite thick, and that's the same sort of thing. So when you have a lower pressure in the suit, it's easier.
In Canada, it gets very cold. We're very familiar with wearing a lot of layers and jackets and not being able to move. So
that's the same thing. You're all astronauts then.
Yeah. So again, since Dr. Atias is a bit limited for time, we're gonna move straight to her. If you have any questions as they're raised, please use the Q&A tool, and Dr. Ganze can answer them too, and we can also address them at the end also. So I'll invite Dr. Atias to share her screen as she talks about some of the countermeasures that are being used to alleviate some of these issues.
Thank you very much. Thank you for the introduction. I'm hoping that you can see that all okay.
Yes, we can.
Great. So firstly, thank you to Birgitte as well. You have set the scene very nicely for my talk. I haven't actually made a slide specifically about myself, but I think it's useful just to give you a bit of a background as to who I am. So my initial academic background was in sport and exercise science. And then I moved over to do my master's in space physiology, but still during my my research from that master's, still with an exercise physiology focus. And then I was fortunate enough to obtain PhD funding to continue with the research that I started during my master's, which I will touch on today within the talk. And then after I finished that, I was placed at Manchester Metropolitan University with Birgitte for a postdoctoral position looking at neuromuscular deconditioning during 60 days of bed rest and the potential effectiveness of artificial gravity to mitigate that. But I'll go into that a little bit more later as well. So first of all, I think it's important just to understand a little bit more about why we need countermeasure training. Birgitte has already explained to you some of the issues that are encountered in space from a physiological perspective. And of course, there are a multitude more. But what we essentially need to do is try to create the fundamental element which is lost, which of course is gravity. So gravity under Earth conditions provides us with a valuable loading stimulus to muscles and bones, so that when we walk and we move, we're continuously using our muscles and our bones to be in contact with the floor and to push off from the ground. So when that's lost, we see adaptations to the musculoskeletal system, for example. We also need countermeasures to frequently activate the cardiovascular system. And as we've been told by Birgitte, this is really important because that system gets weaker because it doesn't need to work as hard. And we also want to be able to maintain the general movement and neural patterns of the individual so that when they return to Earth, resuming these activities is not so alien, excuse the pun, to them, and that they're able to resume their normal activities of daily life with as much ease as they can. Finally, we need our crew to be able to remain fit and healthy for a number of different purposes, both during flight. So if somebody needs to participate in an extravehicular activity, for example, typically those activities can last hours and hours, and there needs to be an element of endurance there. But also in the case of any kind of emergency egress, the individuals need to really be kind of fit and healthy to be able to respond to those demands. There are a number of countermeasure difficulties at the moment, which the crew currently face. A lot of that actually comes down to crew member, the amount of time that's required from the crew member to participate in those. But also there's inevitable space restrictions. There's only so much you can actually fit on board a spacecraft, and the same with volume and power. There's only so much power that something can be able to generate, because if it's that much and something vibrates, for example, then it can actually push the space station off of its trajectory. So we need to make sure that these logistical issues are taken into account, and also the cost. We don't have an endless pot of money, so that also needs to be forecasted for as well. Okay, so one of the main current countermeasure devices is something called the advanced resistive exercise device, and it's a little bit like a multi-gym, or like a cable machine in some way, shape or form, or a Smith machine is probably the better analogy to kind of earth-based gyms. And you can perform a multitude of exercises on this. The way that this works, obviously, is not via weights, but it uses air pressure to simulate loading, or that the crew can push against. And that you can really replicate most exercises that you would want to on here. So lots of different compound exercises like squats, lunges, deadlifts, and so on, but a number of upper body exercises as well. And in terms of the prescription, the exercises are generally set per person. So there's no generic plan per se. Each crew member will get an individually tailored set of repetitions and sets and weight, for example, so that they're working at relative maximum effort with each repetition. There are also a number of aerobic exercise devices on board the ISS. There is the CVIS, which is the cycle ergometer from the European side, here on the left-hand side. And then sorry, I should have explained the whole acronym. CVIS is cycloergometer with a vibration isolation system. As I mentioned before, we need to make sure there isn't too much movement of equipment. So the cycloergometer minimizes that, as does this treadmill. So this is TVIS, also with vibration isolation. And you can see that the individual is wearing a harness, which is attached to some bungee cords, which is then anchored to the treadmill to essentially pull them down onto the treadmill belt. And at the moment, it's possible to replicate about 70% of body weight loading during running on that piece of equipment. And then there is the Russian Velo, which is the Russian equivalent of the cycloergometer also. So the general requirement for exercise actually changes ever so slightly between the European astronauts and the Russian astronauts. At the moment, the ESA and the US training plan is to do 6 days on and 1 day off with 2 exercise bouts per day, which is really quite taxing. And they normally have 1 session of an hour and 1 session of an hour and a half. And that will be comprised of some form of ARED activity, so the resistance side of things, and some form of aerobic activity. And I mentioned just before about everything being tailored specifically to the individual. And the Russian routine is ever so slightly different. They have a a program of 3 days on, so 3 days worth of exercise and then 2 days rest, and 3 days on and 2 days rest, and so on and so forth. I think at this point, before we go into any data, it's really valuable just to introduce you, in case you're not aware, of some of the most commonly used spaceflight analogues, because as I'm sure we can all appreciate, it's really quite difficult to continuously test people on board the International Space Station. And that number of people is also limited to a handful of people per time. So we need to be able to have these Earth-based analogues where we can do studies to understand what adaptations we might expect during spaceflight, and also subsequently help to develop countermeasures. So laying in bed with your head tilted down by 6 degrees is the most established and well documented. Hind limb suspension is normally done in rodents. So essentially, well, it's quite obvious, you can see there, suspending the back legs of a rodent renders them immobilized. So they are subject to adaptations related to disuse. And then we see a very similar thing if you were to cast or suspend one of our 2 limbs. So that's done quite frequently on the legs. You give somebody a foam boot or the like on one of the legs, and then you're then taller, and then the other leg is free to hang and again be disused. And then we would see similar adaptations happen there. So I'm going to go into some of the countermeasures that are typically used, and a little bit like Birgitte's talk, this is really a whistle-stop tour because it would be impossible to talk through it all. So this is really just a highlight of some of the main topics and where we're at with some of them and so forth. So we have generic countermeasures, which would really help to tackle everything. And then we have some specific countermeasure ideas or countermeasure implementations that would target specific systems or aspects of our health. So the first area is with hormones. And what we have seen with growth hormone is that there has been some evidence to show that it helps to prevent a decline in protein content in the gastrocnemius muscle of rats in that hind limb suspension model, which I showed you just before. But the same equivalent effects have not been found using insulin-like growth factor 1 at present. And that research was really quite a long time ago, and nothing has been done since, which can mean one of 2 things, but typically it's because there's no possible opportunity there. But I could be wrong. I'm not entirely sure where the literature is at with IGF-1. With regards to whey protein, actually, Alessandra Borzuti, who was one of mine and Birgitte's colleagues at Manchester Metropolitan, has shown some beneficial effect of whey protein supplementation during a 19-day bed rest, where it was shown that muscle fiber oxidative capacity, that decline was actually prevented in those that were using the whey protein. And leucine, which is an essential amino acid, has also been investigated during 14 days of bed rest and was actually shown to help promote protein synthesis during that time. So lower body negative pressure is generally for the cardiovascular and hemodynamic system, and to aid with the fixing, let's say, of orthostatic intolerance on return to Earth. The device is a cylinder that encloses the lower abdomen region and lower extremities to maintain a controlled pressure differential for extended periods of weightlessness. So essentially the tube covers the astronaut from the feet to the waist, and then an airtight seal is made around the waist. And then you have a pump that sucks air from the tube, which creates a negative pressure inside the tube, and then hence around the legs and the abdomen of the subject. In effect, that's sucking blood and fluid from the upper portion of the body down back towards the legs to help realign the fluid balance. There have been some studies performed using lower body negative pressure in combination with exercise during bed rest, which has been shown to help prevent a decline in leg mass, strength, as well as endurance, and also has been shown to maintain sprint speed and peak oxygen consumption compared to reductions that were seen in the equivalent control group. So with regards to bone demineralisation, there are some specific countermeasures that have been used for that as well. What we really need to understand in terms of bone is that bones stay strong and healthy when they're exposed to impact. So ground reaction forces, constantly moving against a surface, and so on. So we've seen that vibration devices can offer some effectiveness at providing that stimulus, but as mentioned before, with vibration devices, they are logistically challenging for spacecraft, so they're typically not implemented. But far more of a low-cost version of impact can be just to simply jump or use variations in jumping. And there have been a couple of recent studies that have looked at the effect of jumping during bed rest and simulated Martian gravity, which I'll come to in a moment. And actually, Andreas Kramer's group showed that during 60 days of bed rest, those that performed a reactive sled jump, so essentially laying in a horizontal position and jumping, jumping up, but essentially backwards, again, against an air pressure type situation, helped to preserve bone mineral density in the tibia. And we found actually this last study by Weber et al. Was part of my final PhD study at the German Aerospace Center in Cologne, where we had people run on a vertical treadmill. So simulated partial gravity levels ranging from lunar, Martian, and so on. And we found actually that if you jump in Martian gravity at a height higher than 15 centimeters, then you can actually generate the equivalent peak reaction forces that are seen when running at 1G. So that's really, really quite a nice comparison and something that we could potentially take with us to the moon or Mars at some point, that we just need to jump at certain heights, and then we should be able to replicate those forces that we're exposed to day to day during running. There are also some nutritional countermeasures in place. Birgitte will probably know much more than this, but in general, there is a supplementation of calcium to help protect the bones. Vitamin D supplementation is also provided, but that all needs to be through diet because there's barely any sunlight exposure. They see a sunrise and a sunset, I think, every 90 minutes, but in the blink of an eye, it's gone. So that all needs to be through the diet. And there is also reduced salt in packaged foods. There are also other generic countermeasures as well. Might brush past this because there's a bit more that I need to get through. But it's like in a psychological sense, that would require an entire lecture in its own right. It's really quite interesting and quite important. But of course, there are specific countermeasures in place to help maintain their psychological well-being. So they have private family conferences, specified kind of me time, and so on and so forth. And there are other different kinds of analogues that can be used on Earth to help them acclimatize to different aspects of what they might experience in microgravity. So, for example, there are underwater analogues to help them experience the weightlessness and the reduced loading on the joints that they will be exposed to. There is also the use of centrifuges to get them used to the high G forces that they will experience during launch and re-entry. And then there are also some analogues like the ESA cave missions and the NEMO mission that get them used to being in a very, very confined space with other people over long durations and to get used to that confinement. So what would we do in an ideal world? There have been arguments that the most ideal countermeasure would be a human-powered centrifuge to recreate gravity in terms of tackling physiological deconditioning. That combined with exercise would probably be the gold standard, but again, there's logistical constraints with that at the moment. So this actually leads nicely on to the study that Birgitte and I were involved in, but I'll just go through some previous data that was found before that. So more recently, there have been some bed rest studies conducted over in the German Aerospace Centre in Cologne, and they've seen a nice wealth of data really regarding artificial gravity exposure from human centrifugation, which is the big contraption that you can see there. And the exposure is of 30 minutes daily in both a continuous form, so one bout of 30 minutes, and also intermittent, so 6 slots of 5 minutes with short rests in between. And what we've seen from these relatively recent studies is that regardless of whether you were exposed to the continuous or the intermittent artificial gravity, orthostatic intolerance seemed to be improved. Knee extensor and flexor strength, as well as aerobic power, seem to be maintained. That is in contrast to my own research using the human centrifuge, whereby I didn't see any change to motor unit properties. But as with all research, there are generally some reasons as to why that might have been the case. And I'll just dig ever so slightly deeper into that now. So the study that Birgitte and I were involved in was run last year, and we had 24 participants confined to 60 days of bed rest, where 16 of those had artificial gravity treatment for 30 minutes and 8 had no intervention at all. So they were part of the control group. And what we did is assess the motor unit number of the abductor digiti minimi muscle, which is the muscle that allows your little finger to push out. And also the tibialis anterior muscle, which is the muscle on your shin that allows you to bring your toes up towards your head. Our time points were 5 days prior to bed rest, 4 days into bed rest, and 59 days into bed rest as well, so that we could assess both the acute and any longer term changes. We expected to see a reduction in the number of functioning motor units in both of the muscles, but to a greater degree in the tibialis anterior muscle, due to its greater weight-bearing role. And I spoiled it already before, but this is just to show you graphically that there was no change at any time point or in any group in the motor unit number during or over the 60 days of bed rest. This could be related to the fact that we had quite large deviations, or that we used muscles that weren't as susceptible to unloading as others. For example, the participants were frequently able to use their hands, and the muscles of the shin are not as likely to degrade from unloading than the muscles of the calf, for example, which are more responsible in keeping us upright. Okay, I've got a couple of minutes, so I think that I will skip this slide and probably just go straight to this slide just here. So another potential countermeasure, which is obviously a bit more lightweight than a bulky centrifuge, is in the form of elasticated garments. Now, the slide I was just going to show you was about the penguin suit, which is a historical countermeasure with some flaws. But the European Space Agency skin suit is a very similar concept, whilst addressing the flaws of the penguin suit. So what we essentially have is a gigantic elastic band in the form of this garment that gradually increases in tension the lower you get towards the feet, to mimic the loading regime that we experience on Earth. So, for example, at our shoulders, we'll generally carry the mass of our head, and so on and so forth. So by the time we get to our feet, we're carrying everything that we have. So the skin suit aims to give us more of that in elastic form. And the resultant loading is about 20% extra body weight when you're wearing it. So although I don't have the time to go into all of this with you, I wanted to share some of the main findings from adding 20% axial body loading on top of Earth's gravity. From a cardiovascular perspective, we could see that, actually, yeah, sorry, I'll just skip this slide and I'll go straight to this. So from a cardiovascular perspective, hopefully we can see that regardless of whether somebody cycled or ran, the addition of the 20% body loading did not hinder their ability to achieve VO2 max, but the time taken to get there was less. Now, that could be related either to some kind of efficiency type manifestation or a limitation in being able to expand the chest any further and thereby reducing the tolerance time. But either of those are things that would require further investigation. From a neuromuscular perspective, we could see that muscle activity levels changed with increasing intensity, which is just here, but there was no difference between the white and the black bars in either intensity, and that was both with cycling and running. So there were no change to the amount of muscle activity that you used, but what we could observe was a longer activity duration, so essentially a longer black bar in the calf muscle groups during both cycling and running. So the gastrocnemius lateralis here and the soleus down here, compared to normal gravity conditions. So in a nutshell, from 4 years worth of work, what I was able to conclude across all of my studies was that being exposed to this 20% additional loading reduces the time to exhaustion in an aerobic sense, which could possibly be related to disrupted ventilatory mechanics. But the fact that aerobic exercise performance was unimpeded was encouraging and reassuring. And I could also conclude that the additional loading does not increase the amount your muscles work per se, but induces alterations to their patterns. Previous research has shown that the neuromuscular system can alter its strategies to preserve motor output under different loading circumstances. So it may be that a similar situation has arisen here. And finally, really, that the skin suit may have scope as a low maintenance, low power, low volume countermeasure for space missions and also terrestrial populations if we can determine an optimal dose. It's for sure likely that the 20% was too low to see anything profound. So we certainly need more research to see what the optimal dosage is, whilst also trying to avoid any subjective discomfort issues. I'm actually not going to go into this. It was just one slide about my colleague's work, but you can always contact me if you're interested in that. It was actually looking to see how the skin suit could help to minimize the spinal elongation aspect that Birgitte briefly mentioned. But again, you can by all means contact me about that afterwards. And I think I've taken up more than enough of your time, so I will stop there, and I'm happy to take one or two questions.
Thank you very much for that, Julia. That was, again, an excellent overview of some of the ways in which we can adapt to the environment and hopefully overcome it. I guess Edward Ashworth just had a good question on the Q&A, which was looking ahead to the lunar base and kind of long-term settlement on other planets or other systems. Where do you see kind of these countermeasures going in terms of, is it going to be more like training on Earth or the current training on ISS, like once we have a actual kind of lunar base?
Yeah, I think that's a really interesting one. I mean, in terms of obviously the travel there, the craft is going to be tiny. So for sure, there needs to be some kind of, miraculous idea about how to be able to perform a number of different exercises under some kind of loaded situation, whilst taking up a very, very small amount of space. So for example, when I spent some time over in Germany, they were working on a concept called the moon gym, to try and come up with such a compact device that maybe had different bungees here and there and different ways of being able to exercise a number of different systems in one go. When actually on the habitat or within the habitat, I can't see why. But again, this comes back to getting equipment there. It may be that things are sent in bit by bit in a modular sense, like how the ISS was built. But I can't see why certain exercise apparatus can't be sent there and built there, and then they can just maintain themselves like you would in a normal gym here. That would be my initial idea.
Yeah, I think that's a very interesting point, that a lot of the challenges is everything
getting the stuff there
to get there. Yeah, both in terms of launch cost and also transport costs. You're also sending things there in a small capsule. You don't have unlimited size or weight or volume. So it's going to have to be very creative. In terms of muscle muscle kind of wasting or muscle challenges, what's been, or has there been any work at all with kind of muscle stimulation? So apart from, you know, actually exercising kind of the other 22 hours a day, kind of using muscle stim?
Yeah, I don't know exactly about studies on the ISS per se, but there is some there are some research ideas. I mean, I'm not entirely sure how much we know at the moment, but yes, it is in consideration. Yes, there are people thinking of it. Maybe actually, Birgitte, I don't know if you know if there's anything actually been done on the ISS per se, but yes, there are. There are people thinking of it and looking at it. Yeah.
Yeah, actually, the Russians have used electrical stimulation a lot, but they've never published a paper on it. And there's just no paper out there. And we suggested an experiment to ESA last year that was selected for spaceflight testing. And we will, over the next years, try electrical stimulation of the leg muscles. So in a bigger group, and I'm part of it as a co-I. So we'll see what happens. And as the Russians use it frequently, it seems to be promising.
Yes, and I guess it's also a challenge targeting which particular muscles too, especially if it's the postural muscles that may be more prone to atrophy than, you know, for example, the upper body or even the large muscle of the legs.
Yeah, the upper body is really not an issue because you still use it to move around and to hold on to things. So that is not a problem. And some even experienced, stronger muscles in the arms after spaceflight. But the legs are the problem.
Mm-hmm.
And maybe the back muscles as well. Yeah, but now we will only target the legs in this experiment, and then we'll see what it brings.
Of course.
I'm sorry to cut in. I'm sorry to cut in, but actually I do have to leave. I'm really sorry. But I'm more than happy to take any questions. And like Birgitte said, if anyone wants my email address to contact me separately, then please do go ahead and share that. And I am more than happy to take any questions offline.
Yes, well, again, thank you very much, Dr. Arias, especially doing this during your break from work. No problem.
Have a good rest of your day.
Yes, and have a great holidays.
You too. Bye.
So Dr. Gansa is still more than happy to answer any questions that you may have. So
I just see there is a new question actually.
Yes, on the Q&A, and I'll ask it so that everyone can hear it. This one's from Benjamin Marshall, really talking about plant-based nutrition. It's becoming both for environmental reasons and for potentially for health reasons. There's more move to plant-based diets. I guess first part of the question would be, you know, is it prevalent right now in terms of current astronauts? Are there many kind of plant-based diets and astronauts? And then what do you see as the long-term kind of prognosis or the long-term plan and any potential deficiencies that may arise?
Yeah, very good question, actually. Yes, every spacefarer can pick their own food before the flight and decide what they want to bring. And of course, it's possible to only bring a plant-based diet. Of course, some nutritionalists may have some ideas on how to compose it then. And there are super interesting experiments running, for example, in Antarctica at the moment. There's a German research station called the Neumeier Station that currently has a container containing plant growth structures, and they're growing tomatoes and potatoes and some other plants. And it's also a research topic that people look at how to there are those systems where you have fish in the water, and the fish give the nutrition to the plants that grow, and then you eat the tomatoes, stuff like that. I was in Tucson, Arizona last year in the Biosphere 2. And if you ever get there, that's super fascinating because it was an experiment in the 90s where it's a huge winter garden system where people try to build all their nutrition themselves and only ate what they were growing. And it was really hard for them to survive because it showed how much you really need and how many plants you really need to grow to eat, to have enough to eat from that. And we're definitely far away from that with regards to spaceflight because of payload issues and tiny spacecrafts. Yeah, probably there will be some options to grow some lettuce, tomatoes, something like that, but it will definitely not soon be possible to grow your entire plant-based diet in space. But I love the idea. Yeah, and people are definitely hoping for that to come into existence.
Excellent. And Chris, you have a few questions?
Yeah. Thanks for that. I was thinking the last thing you were talking about would be like Matt Damon in The Martian growing a million potatoes. But I've got a few questions, and they kind of decreasing level of specificity. But one of the things that I thought when you were talking about the really pronounced increases in stature is when they come back to Earth, are there any long-term consequences of any of these sort of acute changes?
Yeah, there actually are. I only had 20 minutes. I would have loved to talk about that. Well, what was observed was that astronauts coming back have a much higher probability or likelihood of intervertebral disc prolapses in the neck, but not in the lumbar spine. Strangely, probably the spine is still better contained in the lumbar and thoracic spine compared to the neck. And some astronauts have really reported feeling super fragile and weak. And you shouldn't really bend too much or squeeze yourself into something when you've just landed. You really need all those structures really need time to adapt after landing, and it's important not to be over eager and go straight to the gym and or overdo things. You really need to give your body time. Yeah.
Cool, great. And one thing that's a bit more related to Julia, but you might know. I was thinking, we talk about obviously lots of physiological adaptations and responses, and quite often you see quite a relatively diverse or astronaut population. So they're not like, you haven't necessarily got all long distance runners all look quite similar. So how physiologically similar are astronauts? I know there's lots of pre-selection routines, but are there like strict criteria for physiological responses and things that they must meet to be able to be selected and things like that?
Yeah, so in the initial years of spaceflight, the Americans and Russians or Soviets only picked the fittest fighter pilots they had, and then it became more open. And in 2009, the first space tourist flew, and there were 9 space tourists in space, and I know that their criteria were already much lower than the usual criteria for normal astronauts. Of course, they have to be fit, but there are also some criteria that are not so important to look at, and it's quite known what is really relevant and what is not as relevant. And now that the US have really selected a very diverse set of both sexes, of all sorts of backgrounds, they learn much more about how it's absolutely possible for most people to be in space. And it absolutely doesn't seem to be necessary to have very strict criteria in most fields. So yeah, for example, when it comes to the heart, a lot of people often thought, oh, it must be, we can't bring people with heart disease to space, but actually there's unloading of the heart and the heart needs to pump less. So it doesn't seem to be that much of a problem while in space. Just, I mean, the launch and landing and all the stress is a big deal, of course. But yeah, I think we're learning more about the criteria, and the big step in medical evolution will be the moment when more space tourists will go to space, and when a bigger variety of people with diseases maybe will even be allowed to go. And there is still a huge knowledge gap there on what is possible, or who should go and who maybe shouldn't. Also because usually when you have a disease or something, or a condition, you need a big number of people to do something to see how many % of them will have a problem. And this knowledge is absolutely not there. And it's also not possible to get that knowledge at the moment. So yeah, we medical doctors are really excited to see more tourists in space, just to learn about these things a bit more. Yeah, thanks for asking. Super exciting.
I guess as the technology advances as well, like the suit's going to facilitate more people to travel because the stress is going to be mitigated to some degree by the technology.
Yeah, I mean, the medical things I talked about, for example, the back pain or the nausea and vomiting will still be there. It's possible to give medication, of course, but that is still, it's there. It's also going to happen to everyone, just more or less. Yeah. But of course, there will be new advances and developments to help. Mm.
And the last question was, which was really general, it's just thinking that so environmental physiology, it's relatively easy to do, thermoregulation research. It's relatively easy to do hypoxia research. What would you say are kind of the ways to get into space physiology as what pathways are there into doing it?
Yeah, so I used to work at the German Space Agency, so that was my way into it. But now I'm also working in a university, and the way we get access is by responding to announcements of opportunity from the European Space Agency or NASA, and also the Canadian Space Agency or JAXA, the Japanese. So most space agencies have those announcements of opportunity, and usually they are open for a certain field of research and for a certain project, for example, for a certain bed rest study with a defined countermeasure, or every 5 years or so, it's possible to put in suggestions for ISS experiments. That's what we did last year and where we were successful. It's usually really quite a matter of luck to get in there because they get tons of applications. But I think if you want to start into the field, the easiest thing is to apply for parabolic flights. So the European Space Agency has a continuously open call for parabolic flights. And yeah, it's relatively easy to hand in an application in the first step, and then you need to develop it further with them. But I think if you want to start into the field, that's the best thing to do.
Okay, thank you.
And also the coolest thing to do, maybe.
Yes, no, it's great advice, Dr. Ganz, especially for some of the kind of younger scientists in the audience who, again, there's a lot of kind of other environmental research, but it almost seems like a secret society sometimes for space physiology research. But yeah, that's that idea.
It's quite open. It's quite open for everyone. Mm.
That idea about especially targeting parabolic flights is especially kind of interesting, to really kind of way of fairly quick turnaround, getting your foot in the door and in the field. So yeah, no, that's excellent. Today, do you have any kind of questions you want to raise?
Yeah, maybe I can just pose Birgitta one like speculative question. So what would be what do you think is the hot topic in space physiology now? And I'll rephrase my question. So what if you were given by ESA, I don't know, open hands, what you want to do now, what would you do?
So because I'm a musculoskeletal scientist, so okay, I would only do musculoskeletal. No, just joking. Yeah, the biggest and most important questions that are now to be answered are the radiation question, because we have no idea. Of course, there were radiation sensors on the probes going to Mars, so it's roughly known what types of radiation there are and the intensities and energies, but it's quite unknown what that does to the different tissues in the body. So that's really important research. And then another thing, so the eye problem is already tackled, but another thing in my eyes that is the most important and has absolutely been overlooked so far is to do more research on medicine in spaceflight, because nobody has ever done that, as it was always possible to return within a few hours from the International Space Station or from other space stations. And there was no need to do space surgery, no need to do any medical interventions up there. But when we send people to Mars, it's going to be a 2-year trip or 3-year trip. And if something happens on the way, there need to be solutions developed how to treat these people. And also laypersons need to be able to treat other laypersons. It's like you can't always have a specialist with you. And I think that's the major field that really needs to be tackled, also to be ethically okay, because in our modern internet world, we'll all watch them go there, and it's going to be like, yeah, we all constantly see what they do, more or less. And they're going to be our children's heroes. And when they die of an appendicitis or something stupid that could have been prevented, honestly, that's quite silly, isn't it? And we want to prevent that. And so I think that should be the focus, because we know a whole lot about physiology already, but this is what we really need for the future. Thank you for asking.
Yeah, no problem. Maybe just an add-on to that. So obviously there's lots of talk about this deep space exploration and Mars missions, etc. But what is your take on how far do you think we are in terms of actually getting people there, if you don't consider the financial constraints and, you know, in terms of the technological and, let's say, scientific level?
Yeah, well, technologically, somebody could just go and do it. If somebody just decides to do it, I think there was a really good window to do it, because, you know, of the constellation of Mars and Earth, sometimes coming closer, sometimes being further away. I think 2 years ago or so, it was really close, and it would have been easy to do it then. I just think if people wanted to do it, we might see somebody just do it, like maybe Ellen or somebody. But I don't think it's clever to do it now, because so much knowledge is missing that should be developed, because a lot of engineers and physics just don't look at the human side. And as I said, the medical part is totally not developed. Totally not. There is a first aid kit on the ISS, and that's it, more or less. So I would think that ethically it's a bit more responsible to go when this is all there.
Okay, thanks.
Great. Yeah. Well, thank you so much. I completely agree that as I was kind of revising my book chapter for the textbook, that I really couldn't find anything about, you know, the actual.
No plugs.
No. But in terms of space medicine, in terms of, like, how do you do surgery, or even, not even complex surgery, but, you know, some very basic medical interventions. How do you do that? And I didn't really think about it until you pointed at the start about the idea of, you know, what if you run out of medicine? You know, you've devoted all of your medical resources to one individual. Now you have no backup, you know, and you're still heading towards Mars, and there's no quick, easy way back. So yeah, those questions are kind of very complex in terms of triage.
There's no knowledge about pharmacokinetics or pharmacodynamics, and radiation destroys the medications. So also when you take enough medication, it's totally unknown which chemical structures survive the radiation until the end of the flight and which don't.
Yeah, well, again, it's been just fabulous talk, Dr. Gansa, and I'd love to take your space medicine course, or if you want to give it to us and come back to talk about radiation, talk about some of these ideas in space medicine.
It's already. Yeah, I'd love to do that. Good.
Right, let me just share my screen. So again, that was a wonderful combination of talks, and I think discussion too about some of the many challenges of spaceflight coming up, especially as we move beyond low Earth orbit. So just to finish up with some of the upcoming talks, in 2021, we have 5 already lined up for next year, starting January 7th, and again, running every other week. We'll have, again, a wide range of topics, everything from sweat and skin measurement, temperature measurement on January 7th. January 21st, we'll be talking about hydration physiology, especially in females. And then in early February, we'll have talking about jet lag and especially issues with multi-time zone travel and how to overcome those issues. And then another topic that we'll be going to from the outer space, we'll be going underwater in February 18th on free diving physiology, looking at breath hold divers. And then March 4th, we have, again, a very special guest, Alex Hutchinson, the exercise science, sports science journalist. And he's going to be talking about kind of ideas about sports science and especially science communication. And the title of his talk is What I Wish Scientists Knew About Science Communication. So I think it'll be a great discussion about how we as scientists can translate our knowledge, not just to other fellow scientists, but really out to the greater world. So those are some of the topics that we have coming up. And if you have ideas for whether it's speakers or topics that you want to hear from, please contact us. The email is icee2021@gmail.com, or else at ICE2021 on Twitter. You can direct message us and we will try to follow up on that. So again, I just want to say a huge thanks to Dr. Gansa and Dr. Atias for today's talk. And on behalf of Chris Tyler and Tadej Debovic and myself, I just also want to give a shout out to all of the speakers that we've had over this series. I think we've certainly enjoyed organizing them, and they've been very popular, both among scientists and among students. So I want to thank all of the speakers for doing that. We're looking forward to having bigger and better next year. So in the meantime, again, hopefully we'll see some of you at the Environmental Physiology Social and Trivia tomorrow afternoon. And otherwise, have a terrific holidays and safe holidays, and we will see you in 2021.